We have with us Andrew Norris, data scientist at Brainpool AI, who will discuss creating tools for early phase carbon estimation in the building industry.
Hey, thanks, Senda. How's it going?
Good, how are you?
Yeah, I'm ready to go. Cool. Hi, my name is Andrew Norris, and this is carbon cataloging with large language models. I'm a data scientist at Brainpool AI, and today I'm just going to run through some stuff we've been working on as a proof of concept in the carbon calculation space. So I'm going to introduce kind of my experience with Speckle over the past couple of years, going to outline the pipeline and some of the issues we had with the pipeline that we were trying to solve with this, some of the tools we used to actually implement this, and then the two specific issues, which were material mapping and cataloging, that we can try and solve with large language models. Then we'll kind of summarize what we've learned during this whole journey, and I can answer any questions that people have. So I've been working with Speckle through the Carbon Fixers app and the Quebec Wood Export Bureau for the past 3 years. We first started using Speckle as sort of a visualization layer for our early phase carbon estimation tool. It was a project that we were trying to get people to upload building assemblies to a platform so that we could use them in comparative carbon estimations. Since then, we've done some work implementing with Building Transparency's EC3 API as our EPD source. But this summer, I was tasked with building a proof of concept pipeline for American Structures. They had this massive catalog of walls, all of them very slightly different, maybe a different number of studs, different number of sills, different number of top plates, but mostly the same. But they wanted a way that they could read in these walls individually, save them to a database alongside the carbon costs associated with them. And so this kind of got me thinking on the idea that most of the work I've been doing in Speckle over the past couple of years has involved a lot of manual mapping of data. Just when we're working with industry on an industry level, we don't have that much control over the data that gets sent to us. So we have to kind of work with what we got. And that means that we got a lot of messy data. So I wanted to build something that was a bit more agnostic to the data itself. And I had the idea of using large language models to do some of the processing on that. So for background, an assembly in this context is just a single repeatable product in the construction industry. So this wall here would be an assembly. You can sell it as is from American Structures, and then it will have the same components every time. So it makes the perfect use case for something to apply carbon values to, because you can just do it once and then you have this costed item. So additionally, you will need to know about environmental product declarations, which I'm sure all of you here at SpeckleCon know about. But this is what we're going to be using to actually apply carbon values to our models and our assemblies. We've been using Building Transparency mostly, but we also have played around with one-click LCA at the same time. And then I'm sure most of you at this point know what large language models are, so I won't get too deep into it. But due to the language processing skills of large language models, they provide a unique opportunity to solve some of the gaps in the data that we find when working with non-standard data inputs. So I just want to get into it and start outlining the pipeline here. So the goal of our pipeline is to take an assembly, have someone commit it to Speckle, and then automatically we should be able to pull the material volumes for that assembly, send them to an EPD API such as Building Transparency, get back some carbon costs, and then save all of this together into an assembly database where it can be accessed later. The goal is sort of making a marketplace, but we want to have people be able to upload without someone like me having to go in and manually code the way that their models should be interpreted by the server. So we wanted to build something that would automate that. But we ran into two main issues, which were the data gaps on materials. So in Speckle, we might have a stud that has a material of SPF 165, and that's not really strong sunscreen. It's we think it's wood framing, but being able to make that leap between SPF 165 and an EPD that is contained within the wood framing category in your EPD API is not so simple as just writing. Well, it is so simple as writing a mapping if you want to do it every single time. We want to use large language models to interpret those material names and then be able to map them to categories. And the way we do this is we take the material that we've gotten in Revit and Speckle, and we provide context to it. So we have an external context database that we can help the large language model infer what SPF 165 is. And then we can send that inferred material type to the EPD API and get back our carbon costs for it. The second data gap that we found was trying to actually sort these assemblies into the assembly database. So when working with Speckle, it's not always guaranteed, or building in general, it's not always guaranteed that your model is going to tell you it's a wall. It may just come through as a collection of studs, sheathing, and blocking. And there needs to be some way to be able to say, hey, this is a wall. We can save it with the walls. It'll be used as a wall from now on. And I'll get into sort of the specifics of why that's tough later in this presentation. But I want to go through some of the tools that we used in this project because I think it's useful to have people know what is out there for this. So we obviously use SpecklePy for the Speckle data layer. Speckle's been really useful to us and me specifically as a developer, to be able to access materials and access building components without any prerequisite knowledge. I've never done work in the construction industry. I've never downloaded Revit. But now after 3 years of using Speckle, I do feel like quite confident in the space. So SpecklePy is what we used as our data layer for this. And then we used a haystack for our context converter. So this takes any context that we might be able to provide on our materials and converts them into haystack documents where they will be saved into a database. For this instance, we used Weaviate. So this allows us later to be able to do a semantic search based on those material names to get back some relevant documents and then use those relevant documents as context for our material mapping. We'll use Haystack again for that retrieval process using queries to access the documents. And then finally, we send our data inputs with the context and then a group of classes, which is expected outputs that we might want to get to OpenAI's functions API, and we can get back the desired data class mapping. And then the final step is once we have that data class mapping, we'll have a material category for EC3, and we'll be able to apply carbon cost to it immediately. So cool. So actually on the specifics of material mapping, we can look at what that looks like. So our pipeline has a Speckle commit, and we want to take that Speckle commit, pass it into a parser to get out our material quantities and types, and then create a material mapper to take those material quantities and types, convert them into an EC3 category, and then send it to the EC3 API. So one of the things we faced early on, and what I actually thought this project would be more about, was parsing the materials from the Speckle commits. When you're working with non-standard data types, you end up with a lot of weird nestings. And I think this is across the board, and not just in Speckle, but obviously my experience is in Speckle. But you might end up with materials being under elements, element zero, components, elements, display value, 1. And then it might be under something else the next time. So the way we kind of did this was we built a recursive explorer. So it would look through the Speckle model, try and find any of those material quantities, and then select for ones that were visible. Because a lot of the times we would get materials that weren't part of the actual object, but were kind of sent along with the Revit connectors. And then once we have that material, we built a material database which has all of the context for the different materials that we were using. So for this proof of concept, it was pretty simple. We just took some information from Wikipedia, took some information from the documentation from American Structures, and put all of that into a database for us to search on when we have that material name. And that can provide back some value. But there's definitely more expansive ways you can do this. If you're working with EPDs that have detailed descriptions, you can embed those directly and try and do a mapping from your material name or some additional input by a user to an EPD directly. And that will give you a bit more room to play versus just this kind of simple mapping that I've tried to automate here. So yeah, you can see how this looks here with the material going into a retriever. That query pulls out all the context on the different materials and then will give back what it believes is relevant. Yeah, and then the EC3 categories are the actual data categories that we're trying to map to. So these are classes in this example. And then once we can get the data into these formats, we know that it's usable in our pipeline. So here is the prompt we used for our actual pipeline. You can kind of see it's pretty basic. It's pretty forcing too. We always want it to respond with a category name, and we want it to always respond with something in the category list. So there is room for improvement here, but I do think it's important for when you're working with large language models and when you're working for stuff as black box as this, it's good to post and make sure that you're visualizing and showing every interaction you have with these large language models. So this is what it kind of all comes back together when we get the final pipeline. You can take a quick glance at this, but essentially we pull everything together, the materials, the material context, and the EC3 categories, use those to send to a prompt to OpenAI, and then OpenAI does a mapping for us, and we can calculate a carbon cost from that. So the second issue that we were trying to solve with this, the second data gap, was this assembly type one. So this might seem really simple for a lot of people. When you look at this, it's a wall. I can see it's a wall, you can see it's a wall. If I put this image into ChatGPT, it knows it's a wall. That's a really innocuous data gap, trying to figure out why a large language model can't look at this and tell that it's a wall. But there's some hidden things that we don't really see. So when I was given my collection of walls for this project, I was given all 140 walls in one single Speckle file. And there was no hierarchy to this Speckle file. So it had about 6,000 elements, all of which were just kind of suspended in 3D space in a list that looked like a collection of walls. But if you actually tried to select one of those walls individually, you would have to do it using vector math. You wouldn't be able to just, you wouldn't just be able to pull it out directly. So the wall looks like a wall, but it doesn't actually know that it's a wall. So a lot of times when we're working with data, we find that we're working with these sort of obscurities of what the actual object is. So we can have a collection of elements here, which include like a stud, blocking, sheeting, bottom plate, and that's not sheathing there. So even within the data here, we have some typos that when I looked at this, I don't have 10 years of experience in the building industry. I actually thought for a while that maybe sheeting was a thing, but it turns out it's not. So there's a lot of data gaps even in just the way that humans look at these objects. So you have to keep in mind when you're working with data at this level, like what is the gap there because you're not experienced enough? Is the gap there because the data is incorrect? Is that gap there solvable? And in this case, it was. If you send in a large language model, if you send in a list of objects like a stud, sheeting, blocking, and bottom plate to a large language model, it will be able to identify that this is a wall, as long as it is given the correct amount of context and the correct classes for the output. So this whole project was built on the idea of trying to solve data gaps. I think this whole conference overall has been sort of a experience in figuring out how data gaps how you can solve these data gaps. And I think there's a lot of work being done on the industry level to create standards and practices that are going to be really helpful going forward. But sometimes you're going to be in situations where you're not going to have control over the models that are being sent to you, as I am in this case. And you're going to want to find ways to be able to solve for that. And one of the ways you can do that is with large language models. So when you need to infer values based on some input and you can provide context, then this is a great solution for it. I do want to say that this is still incredibly experimental and a proof of concept and is not in any way meant to be used in production. But it has served the goal of trying to catalog objects for our team. And as a result, we're in a lucky position where we don't have control over the models that come in, but we have experts that can come and review this stuff afterwards. So we're just trying to save a step for those experts to be able to apply the EPDs themselves. Rather, they can look later, and then down the road, they can even provide context to the data. So I just want to finally make another point here about transparent prompt engineering. I think it's always important that when you're working with stuff like this, to post your code, to be honest about what's happening. I don't think that there's any way to really know what's happening under the hood, but there is a lot of ways that we can make what we're doing with large language models very transparent. And I think since it's the building industry, I think we want to be as transparent as possible. Cool. And now I think it's time for any questions, if anyone has any. Yeah, so great question. How has your experience with AI been? Have the responses been accurate? So with those 140 walls, we were able to process them mostly accurately using some fine tuning. So at first it did have trouble identifying what like spruce pine fir was, that SPF value. But the more context we were able to provide to it, and down to the point of even providing like a Wikipedia page on spruce pine fir, it was able to make that inference more accurately to wood framing. That being said, I think there's much more accuracy to be gained in this space. This was just going for a kind of proof of concept, looking for material names to categories, but I do think you're going to want to have down the road material names, some user inputted context, and then send those together to the AI to try and get back a more specific solution or response. But yeah, for the most part, this is able to identify the difference between steel, wood, OSB, and yeah, so cool. I think that's all the questions for now.
Yeah, thank you so much, Andrew. There's no more questions, but you're getting lots of positive feedback. Amazing work. Oh, here's one more. We can cover this one.
Do you use any text to 3D retention techniques for training large language models in the pipeline? So I'm not sure exactly what you mean by this question. So 3D retention techniques, if you could provide some context. But no, most of this was done in a text-to-text mapping situation. So I think there's some work, like I said, with that picture of the wall, you might be able to infer more stuff by looking at the object and sending images of it and 3D models of it. But for the purpose of this proof of concept, we kind of limited it to text to just try and build something that was simple and able to catalog.
All right, thank you so much. We'll see you soon then.
Thank you.